Alright, boom. Nah.
Yo, can you hear me now?
Yeah, I can hear you now, bro. What are you saying?
I was bugging out, but yeah, what were you saying about the integrals with the
The integral, what was I saying? What was I saying? It's
just want
uncommon. You'll see sine
uh,
squared. Actually, in the 2024 paper, there was a sine squared and everyone bugged. They were like, yo, what's this? But actually, it's that thing was part of the spec. And I
what
was
as
a bit
in ju
surprised.
just integrate sine squared.
Yeah, it was like a bit of a proof behind it. It was like the integral of sine squared 2x.
Oh,
And people were like, yo, obviously some people got it right. And I was like, why did not more people get it right? And it's because the teachers they just didn't focus on it. So you know what? I've actually put it in today's thing. So let's see how that goes. Mm,
sine squared 2x, right?
yeah, yeah,
So you just put it into cos 2x
yeah,
and then just double the
yeah,
thing in the middle. And
yeah, exactly.
that's light, man.
Yeah, but people bugged. They got shook.
Mm, I think you know what it is, yeah. When teachers teach a topic, yeah, the students they don't apply it. They intake it,
Mm,
and then if they see something different to what they've learned in the classroom, they start bugging out.
100%. Because it's about application. That's what maths mostly is. Hi guys. Hopefully you guys can hear me. You know what? I need to remove the waiting room. I've got the waiting room there because I don't want like randoms joining in it.
Mm-mm.
And let me see if I can turn it off. I don't think I can. You know, I'll just wing it. Alright, you guys cannot see my screen right now, but how are you guys doing? You can turn on your mic if you want. I don't mind. Or you can chat in the thing. Uh, there we go. You know what? Might just have to do it like this. Might be the best thing to do like this. Is it like fully visible? How's it looking? Is
Yeah, yeah.
it all right?
We could you not start the slideshow normally?
I've tried that, but the thing is, it wants to go on my second monitor, so it's looking like that, and my display is there. Don't know, you probably can't see that.
Can you not change the screen
I'm
that you're
I'm
projecting?
trying. I'm trying, bro. I'm trying my best.
All right.
Duplicate. Actually, no, swap. Nah,
Yeah.
that didn't work. Duplicate. Right, now it bugged. Yeah, bro, I can't lie. We're gonna have to firm it like this, man. We're gonna firm it like this. You guys got paper and pen ready, yeah? We'll wait like 2, 3 more minutes and then we'll start. Uh, type Y in the chat if you can hear me, or like just do something if you can hear me. Just need to check if mics and everything working. I know Hisham can hear me. Cool. Yes, Sahana. Perfect. Great, great, great. Yes, yes, guys. Let me see if there's any other guys waiting in the waiting room. Cool. I'm gonna be looking like side to side here and there just because of
Mm-mm.
the waiting room, so don't mind that. But as we go through this, yeah, as we start with this, I want you guys to be very, very comfortable. Ask questions, put your hand up or whatever. If you're unsure about anything, okay? Because we're trying to cover a lot of year two stuff. It's not going to be everything, okay? It's not all of year two calculus in today's lesson. It's going to be introduction to chain rule. Some of you will have looked at chain rule already because either you've started year two differentiation already in school or you've just rushed ahead, which is completely fine. But either way, we'll be looking at some nice stuff. And you should, by the end of today, should be able to hopefully, let me find it, differentiate this mess. Okay, so don't. I know it looks scary at the moment, yeah, but you'll differentiate it very, very soon. Okay. You know what? Let's. Should we start? One more minute. Let's do one more minute. If you want to unmute your mic and just say hi, like I don't mind that as well, guys. How long is this? Very good question, Naylor. I'll try and make it like 1 hour 30. It might be a bit less, might be a bit more, but like 5, 10 minutes. And it is getting recorded. So if you need to leave early, that's completely fine. And I'll email the access to it to everyone afterwards. Uh, let's see. Subslide show. Let's see if I can fix it like literally in the last minute. Oh, yo, I've done it.
Have you?
Yes, I'm a genius. I'm a genius. Crazy, crazy, crazy. It's great. You know what? Let's do it. Let's start, guys. Okay. Welcome to U2 Calculus. Um, Make sure you have your pen, paper ready. Some of you guys said yes. So you guys are active, which is nice. Okay. Who am I? As a quick introduction, some guys you already know me, some of you won't. Half of you guys are here from TikTok, half of you guys are here from LinkedIn. I'm Anas. I'm an A-level maths tutor. I'm in a gap year at the moment, but I got 3 stars and an A in this 2024 exam period. I got 94% in my maths. You probably heard the maths grade boundaries were absolutely crazy high. I promise it wasn't my fault, but I got 94%. I've got 2 years, 7 months of teaching experience now. It's like almost November, so you can call it maybe 8 months. Let's just call it 3 years for the sake of it. Why not? Oh, you might want to join. But you might be like, okay, how does this guy already have 3 years of experience of teaching? I started teaching in March of year 11. So I was before I started teaching actually, I was doing my GCSEs while tutoring. And then during my GCSE time, exam period, I was also teaching throughout that time. I took a bit of time off for my exams. I was teaching in like a center, GCSE at that time. And then afterwards, year 12, year 13, I started doing A level and more GCSE. And now I'm here today. Okay. So, what we're covering today, hopefully, we're going to cover some parametrics by the end of today. We're going to do some differentiation and integration from year 1 as a quick recap. And then we're going to look at the chain rule, differentiation, integration, and then we're going to briefly look at like product rule and quotient rule. I feel like those type of stuff are not too important because at the end of everything, at the end of the day, you're going to be really falling back on the chain rule. So it's the basics, the base of year 2 differentiation is chain rule. You guys can't see anything. Oops. That is my fault. That is my fault. Thank you, Rosie, for letting me know. All right, hopefully you can see that. Can you see that now?
Yeah, yeah, yeah.
All right, calm. Let me know if there's any issues. Yeah. Perfect. Perfect. Okay. This is my prom picture actually. Let me go back. I'm very proud of this picture. That's me. But yeah, cool. Let's move forward. So, as a recap, just from year 1, I want you guys to have a quick differentiation and integration of this. I'm sure you can just quickly do in your head. But we'll quickly go through this anyways. I'll give you a minute or two just to have a look at this. So go for it. Okay, if you know what you're doing with part A and part B, I say skip those. Part D is not too bad actually. In part E, we'll look at that as well. Okay, I'm gonna check if the pen is working. Yes, it is. Great. Let's change this to black. So you know what? Let's just do it together. We differentiate 5x cubed. This goes to 5x. No, it doesn't. It goes to 15x squared minus 4. Easy peasy. What's happened? We've got 5 over x. We'll convert this to 5 to the x minus 1 minus 6x to the 1 cubed. And then we're going to differentiate this. This becomes minus 5x to the minus 2 minus, we're going to times the indices by the coefficient. This becomes like so. Okay, make sure you're asking me any question throughout this whole thing. Oh my days. Okay, it's going to do that a lot, I feel like. That is not good. Let me see if I can fix that. Guys, this is my first time doing this, so don't mind. Okay. Sin x, what does that differentiate to? That differentiates into cos x. Okay, we've got this next part here as well. Now this one, you might have the instinct if you already learned it to do quotient rule. Don't do quotient rule with this. Convert it into index in your indices form. So I'm going to separate these out into 2 fractions like so. And then you might be able to see, okay, look, this actually simplifies a lot more down. And then that means you can differentiate that very nicely. So I'm going to actually convert this left side to a nice differential like so, index form. And this becomes like that. And then you can differentiate this like normal. When we differentiate this, this will become minus 5x to the minus 3. You can use your calculator. I'd actually encourage you to use your calculator. with these. And if you have your CG50, I actually really recommend you get this chunky calculator. Let me find my chunky beast. This will save you in your A levels. Some of you have it, some of you don't. I told Reeb to get it. I'm sure he's yeah, there we go. Yeah, I'm telling you, it saves your life, man. Especially when you do trig as well. 5 cos x. What does that differentiate to? Why sin x cos x? So okay, now that's a very good question. So sin x, I'm assuming you haven't learnt trig differentiation yet. So we'll look at why sin x differentiates cos x. I won't go through the proof through first principles. I was gonna do first principles. Yeah, nail it. But I think it's best to just show it graphically because, well, let's see where the gradient is 0. So you might have looked at it in terms of other graphs. So, well, dy by dx just represents the gradient of a line, right? Well, the gradient at here and here, this is a terrible color. Well, those 2 points is 0. It's because it's a flat line. You can see this here. At those 2 points, it's a flat line. Okay? And that means that when it's a flat line, that means that at this point, your dy by dx must equal to 0, right? So if your dy by dx is 0, that means your dy by dx graph will intersect at these 2 points. Yeah, it is a formula. But I think it's just good to have a nice proof behind it graphically as well. And you can see that this is actually your cos graph. I feel I've drawn that a bit wrong, but it ends up being your cos graph when you do your dy by dx graph. Okay, there is your first principles proof behind it. I feel like that is actually quite long because you have to look at the small angle. I don't know why. I just can't draw the cos graph for some reason. It is like that, isn't it? I'm tripping. I'm actually tripping. It looks like that. That's just cos graph. Okay, so similarly here, if you learn this sort of pattern, your sine goes to cos x, your cos x goes to minus sin x, and your minus sin x goes to minus cos x. Okay, and this is kind of your wheel that you'll start to follow, and minus cos x will differentiate back into sin x. This sort of rotation, you can call it a rotation, it's very, very important. You'll see a lot. Okay, sin x differentiates to cos x, differentiates to minus sin x, differentiates into minus cos x. Okay, so using this here, cos x will differentiate into minus sin x. So this will differentiate into minus 5 sin x. Okay, and that's our dy by dx function. Okay, good question, Rosie. Cool. Now, chain rule. Let's start with some chain rule. Now, what the chain rule is, basically, is when you have functions like these, you might be like, okay, maybe I should expand this out first. Maybe I should do some other method, okay? And you're doing the expansion with binomial or whatever, it can be a bit long. So, to make this really, really easy, we're going to use something called the chain rule. Now, the chain rule basically means that, okay, why can't we differentiate this normally? Okay, for example, if you have 6 x to the power of 6, why is this not the same? Well, here we differentiate this to 6 x to the power of 5, right? Well, why is this not the same thing as this? Well, this part is actually a very, very important part of this, but we also have to add something after it. Okay, and we're going to do the proof of that right now. So there are 2 methods. Today I'm going to show you both of them actually, but I kind of want you to learn it to do it in your head. Okay, I'm gonna get rid of this. Let's just scribble that out for now. Let's say that we have y is equal to 5x minus 1 to the power of 6. Okay, that's my starting formula. Now with this, I'm gonna use my inside brackets, the inside bit, and I'm gonna say, okay, u is equal to this. And this is how your school will teach it. Okay, they're gonna tell you to, okay, do the inside bit as u, and they're going to tell you, okay, all the time use chain rule. I say no. You're going to do it in your head. I'm going to show you how to do it in your head as well. We're going to differentiate both sides. Now, we know that y is equal to this, and we've kind of stated that u is equal to this. We've just brought u out of nowhere, basically, but we've just kind of made a new variable. So I'm going to say that y is equal to u to the power of 6. I'll differentiate this like normal. So I end up with dy by not dx. In this case, it's going to be du. It's going to be 6u to the power of 5. Okay, and you can see this is where it kind of looks similar to this. Here, I'm going to do the same thing because we, as our final answer, we want dy by dx. In our original equation, there's no u. So you want to turn the u back into an x. So du by dx. What's du by dx, guys? Easy question. Du by dx.
5.
5. Nice. Good. You're gonna have to, guys, you're gonna have to firm the PowerPoint. It's bugging, man. Really don't know why it's bugging. Okay. Now, treat it like fractions. We want dy by dx. We've got two kind of fractions. They're not fractions, but you can treat them like fractions. Okay. dy by du times by du by dx. You can see that these two bits get cancelled out. And that makes dy by dx. So if we times these two together, this makes 30 u to the power of 5, which is 30. We bring this back in, 5x minus 1 to the power of 5. Okay, now what is the relationship between the 30, this 30 here, and this original thing that we theorized? What is the relationship between these two? If you already know, don't say. What is the relationship between these two? You can kind of see what we've kind of done. So you've got the 6u to the power of 5, which is this. Where has the 5 come from? Anyone know?
It's the derivative of the inside bracket.
Yes, it's a derivative of the inside bracket, and we're timesing it by this. So if you're going to do this in your head, what we're going to do, differentiate it like normal. Okay, we differentiate it like normal, treat it like your normal function, and then we times it by the inside differentiation, and that's just 5. Okay, and that makes it like so. Okay, your school is going to teach you to do this. They're not going to tell you to do it in your head, because when you get to more complicated stuff, you want to be able to do it in your head, because you don't want 3, 4, 5 different chain rules on your paper when you should be able to just do it in one step. Okay, because this thing and this thing here is going to give you the same amount of marks. Okay, so why not do it quicker? So let's have some practice. Let's have some practice with this one. Try same thing. I'm going to give you guys 1-2 minutes. If you have any questions for the previous stuff, definitely ask. Okay. Hey guys who just joined. I've just seen you guys in the waiting room. Let me see if I can turn off the waiting room so you guys can automatically join. Nila, I'm not gonna say yes or no to that, but good. Very quick. That's very, very good. You guys do the same thing. We're differentiating this. I'll quickly go over the chain rule, so if you've just missed it. Let me see if I can turn off the have you missed anything important? We've just started chain rule, Hassan. Just started it. If you don't know chain rule, I'll go through it like literally right now. But don't expand this. Okay? Don't expand it. I'm just trying to turn off there it is, meeting settings, waiting room off, save. Okay, so you guys that will join should automatically enter. Okay. Good, we got 2 thumbs up on that. Nice. Good, good, good. So what you did, you times it by 4 times 3. Good. Just your normal differentiation. We're going to reduce 1 by the power, and then we're going to times it by the differentiation inside the bracket. X squared plus 1 differentiates to 2x, and this will go to 24x. X squared plus 1 to the power of 3. Well done, guys, if you got that. Easy peasy, yeah? Any questions on that? Any questions? Hassan, if you've missed chain rule, what we're basically doing, we're just differentiating like normal. For example, if you have 3x to the power of 4, this differentiates to 12x cubed, which is this. Okay, but then you're also going to times it by the inside of the bracket. Okay. Now, ln x. ln x is slightly different, okay, because it's a different function. It works with ease. And I'm going to show you a quick proof, and it's a very, very small sneak peek to implicit differentiation. And I'm going to show you the proof behind what ln x differentiates to. So let's say y is equal to ln x. I'm going to e both sides. So I end up with e to the y will equal to x. So this ln gets cancelled out. And then I'm going to differentiate the whole equation. And this is implicit differentiation. We're not covering it today, but it is part of year 2 calculus. So e to the y differentiates to what? Just off the top of your head, make a quick guess.
E to the y.
E to the y. Good. But because it's implicit differentiation, because you're differentiating a y, you also have to times it by a dy by dx. There is some reasoning behind it. It comes with composite functions and stuff. I won't go over it today. But if you're differentiating a y, it will go to dy by dx. Okay. What does x differentiate into? 1.
1.
Good. Now we want dy by dx, right? So that means that dy by dx must equal to 1 over e to the y. But we know that y is actually ln x. So 1 over e to the ln x. What's that? If you simplify that.
1 over x.
1 over x. So the differentiation of ln x is actually 1 over x. And this fact you need to know. It's not going to be in your formula book. Learn it down. Get it down. Okay? This fact you'll see a lot. You'll see a lot in your A-level stuff. But we can apply the chain rule in a very, very similar way. So if you're in a situation, okay, I don't know how to do it in my head, fall back onto that chain rule stuff that we kind of did with the dy by du and du by dx. Use that over, it's not 1 over x squared. Good try, TP. It's not 1 over x squared. Very good attempt, though. There are 2 ways to do this. One way, Naila, you are correct. But there's 2 ways of doing it. One way, use chain rule. 2, you can use your log laws as well. I'm going to go over the chain rule method first. And I'm going to show you how Naila got what she got. So if we use u is equal to x squared again, and y is equal to ln x squared, and we're just going to sub this in again. So we get y is equal to ln of u. Okay. We'll differentiate this. So you get dy by du is equal to 1 over u, which we worked out in the previous slide. And du by dx gives you 2x. Now you can multiply these two together, and you get what Naila gets, which is 2x over x squared. And you can simplify this to 2 over x. There's another way. Use your log laws. We know that ln x squared is equal to 2 ln x. And now we can differentiate this the same way that we've done it. Okay, there's multiple ways of doing the same thing. And you might actually notice a trick as well. If you notice something, let me know. Okay, and this becomes 2 over x. Now to do it very, very quickly, because as I said, I would like you to do it in your head. What's the relationship between ln x squared and this? And we know that obviously ln x goes to 1 over x. What's that sort of relationship? It's some sort of differentiation relationship. Try to see it. Spot it. You got this. If you spot it, type it in chat. Okay, because this you can do in your head as well. Okay. And as you do more practice, yes, Naila. Perfect. So the bottom is your original. The denominator is your original. And your numerator is your differentiation. Okay? So this you'll be using a lot. So I'm going to give you another example. Ln of 3x squared plus 5. Go. What does that differentiate to? Okay, using that fact. And then we'll have a go at some actual exam style question as well with this. I don't know if it's with ln x, I can't remember. Okay, try to do that in your head. Okay, do in your head. You got this. Ln x, the top is the differentiation version, the bottom is the original. What is it? Beautiful. Beautiful. That's my Yorkshire accent coming through. Perfect, guys. You got it. Okay, 6x over 3x squared plus 5. Okay, that's what this differentiates into. Good. Now, practice. Practice makes perfect. What you want to do with these, I'm going to give you a quick hint. Do this in your head and convert them into index form. Okay, have a go. See what you get. And move this to the side. Go. Index form. By index form, Tammy, it's fine. I know you did direct message me, but it's okay. Index form, I just mean 3x minus 7 to the power of a half. Okay. That's what I mean by index form. Thanks. Whoever that was. They let you draw it. Don't draw, yeah. Don't draw. Oh, that is an ugly pen. Don't like that. Nice. Looks good. Do the same for the other one as well. I'll write this as index form as well. 9x plus 1 to the power of minus a fifth. And see what you get with that. First one, that becomes 2 times by 3x minus 7. I'm just showing that working out, so do not worry. And you times it by, that should be minus half there. Times it by the differentiation. This becomes 6, 3x minus 7 to the power of minus a half. If you're unsure what I did there, okay, I've just differentiated like normal. So I've times the power by the coefficient, and then I've times by the inside differentiation. Next one, I'm going to do the same thing. Got minus a half, it's going to be minus 2 over 5 first. And this becomes minus 6 over 5. Times it by the inside differentiation. Got 9. Can we go through CG50 calc tricks? Hopefully. I'll see if I can bring up the calculator. Okay, so it doesn't want to cooperate. It really just is. I don't know why it's bugging. And normally I do it on OneNote. That's how I've been doing all my lessons. So this PowerPoint, yeah, it's a bit clapped, but whatever. And then you simplify this, and you should end up with this. I'll try my best, Naylor, if I can bring up the calculator, because it's been a bit dodgy as well recently. Okay, cool. Any questions on that? Very well done, guys. Cooked. Absolutely cooked. Picked up on it very, very quick. Okay. Now, I don't know why there's a 4 on the screen. Let me see if I can remove that. Okay, good. Now, with these are the type of questions you're going to see. And you can see that doing chain rule is just going to speed up it's just going to help your life, I can't lie. Look, it's 7 marks, okay? 3 or 4 of your marks are just going to come from, I'd say, yeah, 3 marks, I'd say, in this case, is going to come from differentiation. If you can do that in one step, instead of having a whole page of this random chain rule, or coefficient rule, or quotient rule, I don't know why I said coefficient, or product rule, or whatever, if you do it in your head, easy marks. Okay, so convert this again into index form. Normally, people will say, okay, because it's a denominator. If you might have learned the quotient rule already, because it's in the denominator, we're going to do the quotient rule. And don't do it necessarily all the time. If you've got power there, convert it into index form and do it in your head. Okay. From there, we're going to look at how to work out the normal. Actually, this is where the CG50 actually is really, really helpful. Let me see if my calculator is going to come up on screen. I don't think it is. Yeah, long day. Okay, let's just bring up Desmos. Desmos is my guy. Okay, so once you've differentiated it, um, when do we ever need to use the quotient rule? So quotient rule comes in handy when you don't have a power on the bottom. Yeah. Okay. So for example, if you have like x, when's a good idea to use it? If you have like a trig function on the bottom, or if you have a something like this, I think is a good example. If you have 3x like so, here I'd say it's the better option to use your quotient rule. It's because the 3x interferes with that. Okay, I'm just gonna check your differentiation, guys. I'm gonna convert this into index form, like so, and then we're gonna differentiate. So this becomes -6 minus like so. And to be fair, I'm just writing it down for the sake of it, but I'd say do it in your head, and you should get positive 18. Okay, you should get positive 18, like so. Because you got the -3x that differentiates into -3, and you times it by the -6. Cool. And then what we're going to do, we've got a graph. Now, whatever the graph, actually, I'll draw the graph for you guys. So the graph actually looks something like so. Okay, so if you decide to draw this on your CG50, I actually recommend you do, and that way you can actually check. So we've got a point on the graph which is that x is equal to 2. Okay, that's our x is equal to 2. And we want to find out the equation of the normal. So if we have a tangent at that point, that's what your dy by dx actually works out. We want to work out the equation of the line that's normal to it. So in this case, the blue line. Okay, so the steps that we're going to take, first of all, we're going to work out the gradient of the red line. We're going to do the perpendicular version of it because your normal and your tangent are at 90 degrees. And then we plug it into y equals mx plus c, and we work from there. I hope that does make sense. First step, just plug in x equals 2 and work out dy by dx. Okay, at x equals 2. Now, when you do that, you should just use a calculator. I'm going to bring my calculator out. Yes, normal always meets tangent. That's what the definition of a normal is. Okay. So if it's not a normal, if it's not 90 degrees, it's not going to be a normal. So when you plug in x equals 2, you get -18. Okay. That'll be a quick check. Rico, that actually does look quite good, to be honest, just because you got that 18y. Yeah. Okay, and then that's our. You have to show your differentiation steps. What do you mean? You doing this is fine. That's completely fine. That's your working out. Okay. If you plug in x equals 3, that's okay. Because it's a 7 marker, most of your working out, most of your marks actually kind of come from working out your normal point. Okay. Yeah, it's a bit tricky to start off with, and that's why some people will start with the chain rule, or some people will start with whatever. This in itself is the chain rule, and this will class as the method in itself, and you got implied marks as well. Depends, Hisham. Sometimes substitution does, sometimes it doesn't. In this case, it wouldn't. Okay, if you got your quadratic formulas, the places where you get substitution are substitution marks. 1, mechanics. Okay, mechanics substitution, you always get marks. 2, you got your quadratic. When you're solving quadratics, either you factorize or plug into your quadratic formula. It might do. You might be right, Hisham. It might be, but I'd say generally you wouldn't in this case. Two is where you have your quadratic, and where else would you have it? Very rarely, honestly, you don't get substitution marks in differentiation. You really don't. It's mainly working out for dy by dx, and then you might get a substitution mark for y equals mx plus c actually. But we'll see where the marks actually come from. I don't know if I put the mark scheme in this. I haven't. Okay, cool. And then our normal gradient, that means will be 1 over 18. And then we can just use y equals mx plus c. 1 over 18, you can use y minus y1 if you want to as well. Completely fine. And then we want to work out plus c. Actually, before we do that, and this is where I think the marks come in terms of substitution. Where did the minus 18 come from? I've just plugged in x equals 2. Yeah, Rico, yeah, for 1 mark for working out the y coordinate. So we don't have the y coordinate at the moment. Still don't want to rub out. There we go. Cool. So your y, you're going to plug in x as 2 into your original equation. So you get 3 over 5 minus 3 times 2. So when you plug in 2 into your original equation, you should get y is equal to 3. So your coordinate, this coordinate is going to be 2, 3. Okay. That in itself, I'd say I should probably do the substitution here. But that's your substitution mark, I think, in this case, Hisham. Okay. And then we do our y equals mx plus c. 3 is equal to 1 over 18 times by 2 plus c. And c you should get is 26 over 9 I got. Yeah, I got 26 over 9. And then you can times the whole equation by 18. You can do y minus y1, Rico, because it really doesn't matter. But they want your it really depends. I used to do y minus y1, but I used to just lose a lot of marks because of it, because I just never used to just put it into y equals mx plus c. And then I was like, yeah, I'm just gonna switch to y equals mx plus c. So this is just by habit now. But yeah, you can use that. 3 times 18 gives you 54. And if you times this whole equation by 54, I'm just going to rewrite the equation. So this is the y equals mx plus c equation you should have got. And then when you worked it out, you should end up with something like this. I feel like I've done something wrong here. You get 54y. No, that's wrong. Why did I put 54? That's 18y. Why did I get 54 from? Oops. That's a mistake. 54 and 18. There we go. So 18y minus x minus 52 is equal to 0. I think you did get that, Rico. Yeah, perfect. Good. Amazing, Hassan. Nice, man. Beautiful. I'm going to move my chat in the front. There we go. Cool. Are we happy with that? Any questions on that? Most of your marks, most of this stuff, this is year 1 stuff. Okay? The year 2 stuff, the stuff you learned today, most people will be doing chain rule. Do that in your head, make your calculation quick. Okay? Next part. Okay. Let's do some differentiation using sine and e, and I think you could probably do this one now as well now. Okay, good. 3 cos 3x. Perfect. Amazing. Using the same knowledge that you've done. Differentiate and times by your internal bit. Good knowledge, Neela. Don't worry, man. We'll look at the e part. Okay, so let's use some intuition. Okay, with the other chain rule, you were differentiating and then you were timesing by the u part, right? Now, by intuition, what do you think the u in this case is going to be? What's the u? How do I get cos? Sine differentiates into cos. Cos differentiates into minus sine. And minus sine differentiates into minus cos. Okay, and to get 3x, the sine is same, cos is opposite. What do you mean? What do you mean sine is same? The sine differentiates into cos. It's cos is opposite. They swap around in terms of positions. I think that's what you're trying to say. I think. And then the minus cos will differentiate back into sine. Okay. Where does the 3 come from in the beginning? Just use your same kind of rule. 3x differentiates into 3. So you're going to times this whole equation by 3. Okay, so sine x differentiates into cos x. Same sort of thing. Okay. And you times it, the whole thing, by the differentiation of what's here. Okay, that's your sine x. So for example, if you had, for example, cos of x squared, what would that become? What would cos of x squared become? Not minus sine. Yep, that's a good start. Minus sine. What's the relationship between here and here? Does it change? You're getting close. Hassan's the closest at the moment. Hisham, it's not sine cos. You guys are very, very close. It's minus sine x squared. Yep. But there's something behind the minus. Behind the minus. What does x squared differentiate into? 2x. Yes, minus 2x. Perfect. You see this? And that's your chain rule. You doing that as your chain rule. You can prove it using your formula, using the dy by du, blah, 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 blah. I hate that. Waste of time. Use it if you don't know. Okay? But this is the same concept as this and the same concept that we've been doing the entire time. Okay? I'm going to give you one more one with a trick. Try differentiate. I'm going to put this here. You can probably do this one now as well. Try differentiate cos of 3x squared plus 6x. That's really annoying, but try differentiate that. Minus cos x. Minus cos of 3x squared plus 6x. What does that differentiate into? Cos x minus cos x differentiates back into sine, by the way. Okay, kind of goes in a circle. If someone sent a message that you agree with, just put a thumbs up. You got that? Yeah, nice. So we're gonna keep the same inside the brackets. It shouldn't. It's not. It's not supposed to be cos. Actually, it's supposed to be sine. I don't know what put cos. It's supposed to be sine, and then you times it by the inside of the brackets. Differentiation of the brackets. Okay, that's what you should get. Beautiful. Yes, I had. Nice, man. Okay, and then you can just put the brackets around it like so. Good, good, good. Now, when you differentiate e is actually works in a very, very similar way. When you have e to the x, what does e to the x differentiate into? E to the x. Good. Same thing. What does e to the 2x differentiate into?
2e to 2x.
2e to the 2x. Where did you get 2 from? Where did the 2 come from? Bring down the 2. Not necessarily, okay, not necessarily bring down the 2. What have we been doing here this entire time? Differentiate the 2x. Okay? So we're going to do the same thing here. E to the 2x squared plus 1. Differentiate that. What does that become? I don't know how to move this all to the side, you know. Let me see if I can move it. Yeah, I can't move it. Maybe if I do it like this. I had you differentiate the original thing, which is good. Hassan, you're also correct. I had you also correct. But good. Okay. So I had did the original one. Hassan did this one here. 4x e to the 2x squared plus 1. But exactly the same concept. Okay. Actually, I had be careful with the plus 4 bit. Just because and the 8x squared. You don't want to bring down the 2x squared plus 1. You want to differentiate 2x squared plus 1. So 2x squared plus 1 differentiates into 4x. Right? So if this differentiates into 4x, you times it by you stick it on at the beginning, and then times it by 4. Okay, so you're differentiating the index and times it by the original. That's what you're doing in this case. So have a go at the original question. I had again do that. Try the first one again. Tell me what you get using the same concept. I'm gonna rub this this part out here because it's taking up space. Boom. You missed a bit of chain rule, Arib. The Mogul time already. Damn. Can't you do 4 multiplied by 2x squared plus 1? And then put the e back, times it by 4x. Yeah. Yeah, nearly we can. I'll have a look at what time it is. Can't you do 4 multiplied by 2x squared plus 1? Because the key thing with this, Naila, is because you have to differentiate 2x squared plus 1. So you multiplying by the 2x squared plus 1, it won't work in this case. Okay, and we can prove that using the chain rule. The key aspect with this, differentiate this first. Okay. So easy way, keep whatever's there in terms of the e and times the differentiation of this. So that's going to be 4x times by 4, which gives you 16x. Okay, that's going to be your original question. Cool. I'm going to skip the ln one. Have a go with these. I think you can go. You can have a go with these. I know it's Mugger time also as well, so I'm going to have a look at this. It looks from the timing outside. It is actually Mugger time. Yes, Naila, perfect. First one is minus 2x sine x squared. Good. These ones are slightly more different. I'm gonna show you how to do sine to the power of 5x differentiated. But it uses the same concept as when you have 3x minus 1 to the power of 5. Okay, so if you want to have a go in terms of yeah. Can I do the question I skipped? All right, you meant. All right. Only for you. Yes, Naila. Perfect. It is. You are correct. ln, if you want to differentiate ln, you keep the denominator, whatever's inside the brackets. And then we want to differentiate for the numerator. So this becomes, well, we know that root x is x to the power 1/2. This is going to be plus 3x. This becomes like so. Okay. Obviously, you can write this a bit more nicely, but I think this is probably the easiest way to write it. This is actually bugging, man. This is actually really irritating. I'm sorry, guys. But this is your differentiation. Top, differentiate what's inside the brackets. Bottom, keep whatever's inside the brackets. Okay, that's for any ln x. So if you have ln of x squared, well, the bottom stays the same. Top, you differentiate. Okay, Ahad? Or is that Imad? Sorry. If you guys want to have a quick break for Maghrib time as well, completely fine. We'll be back in 5-10 minutes. So have a go with these, and I'll be back in 5-10 minutes as well. Get some crisps, I don't know, get some chocolate. In the meantime, I'll actually quickly put up the answer for this one. Times by cos x. Amazing. You are correct with the plugging it in to the power of 5. So if you just rewrite it as this, you're completely right. And treat it like a function like we have here. And then just times by the inside differentiation. Exactly the same. Great intuition, guys. This is sort of stuff you're going to need when you're doing your A-level maths. Okay? Try it with this as well. Sec to the power of 4x. You're not expected to know the differentiation of sec x. But you've got this. How did I do question 2? This one here. Recall. But you differentiate this like normal. You differentiate like normal, 5 sine to the power of 4x. But then you have to times it by the differentiation of sine x. Hassan, where do you get 1 over sine x from? Explain your thinking. Ikram, for which one are you talking about there? Cos x to the power of -5. Oh, I see what you've done, I think. So what you don't want to do Oh, you've done it like that. That's actually very, very, that's good. I like that. So one sec is 1 over cos. Okay. So you have cos to the power of -4. You can do it like that as well, actually. You can do it like that. But you've got, in your formula book, you've got this, and it will help you. Okay. Sec differentiates to sec x tan x. Okay. So using that, use that to help you. Okay. But if in any situation, I don't think it will come up. I've never seen it come up. If they're like, okay, prove sec x differentiates to sec x tan x, then use that method, convert it into your index form, knowing that, okay, sec is 1 over cos. Okay, and then you can do it like that. And if you actually do it like that, you will be actually you'll be able to prove. You want to do the proof? Okay, cool, Rico. Sure, why not? Sec x. Well, we know this is 1 over cos x, which is equal to cos to the -1x. Okay, and we're going to apply chain rule. We'll use the same method. I think Emad said this. Someone said this in chat. I can't remember who. Well, this differentiates to cos x differentiates to actually we'll do the chain rule bit afterwards. We'll differentiate this like normal. Like so. But then we have to times it by the differentiation of cos x, which is minus sine x. This makes cos x to the power of -2 sine x, which is equal to sine x over cos x times by 1 over cos x, which is tan x sec x. Okay, that is the proof behind it, but obviously that's a lot longer method. I wouldn't recommend doing it that way. You've got this stuff in the formula book, so use your formula book. I think they're actually changing the formula book, you know. I don't know what they're doing it to it because I've searched every time I tried to teach someone, yeah, and tried to bring up the formula book. I can't find it on the original edXL website. I actually don't know, man. I don't know what they're doing it to it. It's just disappeared from the actual original edXL website. So if you look it up, yeah, it just won't come up. You'll see it on like Maths Genie and stuff, or Physics and Maths Year, but you won't see it on the original edXL website. You'll see the international one, but I don't know what they're doing to the this year's one. So good luck, guys. I'm joking. I think I'm sure you'll be fine. So sec to the power of 4x. Any idea, guys? What do you think? Sec tan x to the power of 4. Good idea, Tammy, but it is not. Try use your chain rule. Stay with the same format. I think that is right, Ahad. Can I go through the sign one? Yes, Hassan, I will. So the way you should do these, carry them out the same way we've done it with this. Okay, don't change the rules. Stick with the same rules. First step, differentiate like normal. So this becomes 4 sec cubed x. Then times it by, what's the differentiation of sec x? Sec x tan x. Okay? Then you can leave it like this if you want, but I think you should probably simplify. This becomes 4 sec to the power of 4x tan x. Okay? I think you'd get that perfect. I'd say have a go with the tan one as well. Okay, use the same sort of rule. I'll go through the sign rule really quickly, Hassan. So exactly the same thing. Sine to the power of 5x, you can rewrite it as like so. Sine x all to the power of 5. Yeah? Differentiate like normal. 5 sine x all to the power of 4. Yes. Yep. By the integral of the trig. I mean, I think you mean differentiation, but yeah. Yes, And then what's the differentiation of sine x, cos x? This becomes 5 sine to the power of 4x cos x. Does that make sense, Hassan? But if you're in a situation, you're like, okay, I've forgotten. I've forgotten how to do it in my head. Then fall back using u is equal to sine x and y is equal to u to the power of 5 in this case. Okay, use your dy by du, and then you'll be able to work it out. However, it's like 10 times longer. Okay, but to be honest, I'll show you anyways. And your school will really enforce it. They'll be like, do it this way, show it in paper, show you working out. But at the end of the day, you're gonna get the same amount of marks. This is how further math students do it. And they have so much more time in exams compared to normal math students because they have time to check all the other stuff. You got that? Did anyone else get that? What did the rest of you guys get? Make sure you're asking me questions, guys, if you're unsure. That's why we're here. You guys actually cooking, man. I can't lie. You guys actually really cooking. It is. Ahad is correct. Tan x goes to sec squared. Formula book, bro, is in the top right. I should have mentioned that. But tan goes to sec squared. Keep whatever's in here. Okay, that's the starting point. This is not the final answer. Let's see what you can get after this. Hassan, you are correct. There should be no 2x though. It should be just sec squared e to the x. Okay, but beautiful. Absolutely beautiful. You guys are cooking. Guys are cooking, man. Easy peasy. Easy peasy, right? Light work. I don't know why that stretch thing is there. I'm gonna quickly go over product rule. And this is where your chain rule comes in and doing it in your head. Okay, this is the actual application of it. Because a lot of the time you'll get stuff like this. Now your product rule basically is, you might have covered it in school, like very, very briefly if you started differentiation. What it is when you have two formulas or two things being multiplied by each other. So in this case, we can't differentiate this in our head yet because we've got this x squared in the beginning. But using the product rule, we can separate them out. Now, what the product rule says is when you have two functions, f of x and g of x being multiplied together, when you differentiate that, your differentiation becomes f prime x gx plus f of x g prime x. Don't have to learn, actually, no, you do have to learn this actually. This one's not in your formula book, but I don't like the g of x, so I've just actually simplified it like this. I've personally learned the product rule like this. Okay, so when you are separating them out, your two separations will be, in this case, x squared, and the other one will be your cosec. Now I'm gonna put the cosec differentiation on screen because you don't need to actually know it. Can't remember what it was. It was on the other screen. Cosec goes to. Let me see if I can change this image real quick. Give me a sec, guys. If it wants to cooperate, you guys can see if you have a go with this actually, as it decides to do whatever it wants. I don't know why this is there. This one is supposed to be here. Copy, paste. Perfect. From current slide. Okay, good. And you can see the cosec will go to there. Now your f of x in this case, keep it as x squared. And I actually like to lay it out like so. F in this case is x squared. F prime gives you 2x. And this is where you're doing it in your head. It's so handy because you're just using less space on paper and it makes all your calculations a lot quicker. And this is where do in your head. Okay? Now, you've kind of already got this here, so it can make this a lot easier. Now, use a bit of intuition. They do give you the quotient rule in the formula, Rico? Yes, they do. So here it hasn't got a power. Okay, so it's not the exact same thing as before. However, do you remember that sine of 3x, for example, differentiates into 3 sine of 3x? Using the same sort of rule in this. Okay, so try it. Have a go, knowing that cosec x differentiates to that. Have a go. It's okay to get it wrong, but see where it takes you. I think rather than this, 3... Oh, yes, you are right, Imad. 3 cos 3x, sorry about that. Yeah, Rico, yeah, you're right. Oops, that's my mistake. 3 cos 3x. I think if I write the cosec x like so, I think it might be a bit easier to actually see. I think it might be better to do it like that. Okay. See where it takes you. Same sort of thing. Don't change the rules. Slightly adapt. Okay, the rules follow in the same way. What did you miss? Not much neither, to be honest. We just looked at sec to the power of 4. We looked at tan x. And mainly it's just using your formula book. Why did I get rid of the e? Which e? Which e? On row G. Oh, you are right. I did. That is a terrible mistake. Absolutely right. Hassan did the same thing as me. Yeah, look at that again, bro. I don't know why I did that. That's a bad mistake. That's a bad habit. I did that all the time in class when I was in school. I couldn't even type stuff into calculator properly, man. That's where I used to lose all my marks because I couldn't copy across. So yeah, make sure you're copying across. Thanks for noticing, Rico. Okay. So let's actually start with this. This is the first part, I'd say. So Hassan, you got the right idea. So with this, instead of x, we don't actually have cosec x. We have cosec of this mess here. So I'm gonna actually rewrite this like so. So I've got minus cosec of e to the 3x squared minus 2x, cot of e to the 3x squared minus 2x. Okay, but it's not finished there. It is not finished there. You know that sine 3x here differentiates 3 cos 3x. Where did the 3 cos 3x come from? Why is it not just cos 3x? Why is it not just cos? Exactly, you're differentiating 3x. So we're going to do the same concept here. First, we differentiate the sine into cos, which we've done here. And then we have to differentiate the inside bit as well. What's the differentiation of e to the... Well, that mess there. Okay. The differentiation of e to the 3x squared minus 2x. 6x e to the 3x squared. Yep, minus 2. Good. Yes, Hassan. Perfect. Okay, and this is you doing chain rule. This is a chain rule right here. So in this one question, you've done chain rule 3 times. So imagine doing that manually using the dy by du. You've got 4 du's on the page. Looking long. You're gonna get confused. Okay. I would say I can't lie. You're not gonna get. Yeah, you're right, Nella. That should be minus 2. But yeah, you can see you've done chain rule 3 times here. Okay, so if you're doing this manually, it's gonna cause you a lot of mess. And this is the best way to do it. Ahad, you've sent x squared e to the Is that the final answer? I'm assuming. Yes, it is. That is the final answer. And then your final answer, you would multiply these two, and add together. Okay, I'm not going to do that because has kind of demonstrated kind of a long formula, and I don't think that in a real exam you're going to get something to this extent. However, I've personally seen it as well, even in the 2024 paper. There are situations where you will at least do chain rule twice. Okay, in one question, this sort of thing, you're going to do chain rule twice, and your e to the whatever, that's a chain rule in itself. Okay, and you've learned probably that e to the 2x differentiates to 2e2x. That's doing chain rule. Okay, that's doing the chain rule. So why not apply it to the rest of it? Now it looks really, really complicated. Now on a scale of 1 to 10. Rico, on a scale of 1 to 10, what's your difficult? What's your? It looks really difficult, yeah. But what's your comfortability level? 10 being super, super comfortable, and 1 being I have no idea what's going on. Nice. 6, 7, 7. I'm liking this. Your Rico Aribe as well, bro. Tell me what you're feeling. 10. Yes, Neil. Why did I separate it? Can't it be cosec cot x? Yeah, 10 is easy. 10 is like easy peasy. Why can't it be cosec cot e to the thing? Because of this part here in the formula book specifically. So what we first did, because we know that sine 3x, Arib, ask me questions, bro. You need to ask me questions then. Sine 3x. I'll try to explain as much as I can, yeah. And this is a hard question. I'm not saying it's an easy question. I kind of just made it on the spot. Sine 3x differentiates to cos 3x first, yeah. So we differentiate the sine into the cos. Same thing here. We differentiate the cosec into the cosec cot. Yeah, calm. No worries, Arib. Okay, so sine differentiates to cos, cosec differentiates to cosec cot. Then we differentiate the inside bit. 3x differentiates into 3. The inside bit differentiates into that mess. Does that make sense, Nila? I think Nila asked that. Yeah. Yes, you do, Neil. You get them in the exam. That's from the formula book. Otherwise, I wouldn't have given you them. Okay. The sine cos, you do need to know. So what does the sine differentiate into? What does cos differentiate into? You just need to know that. Rico, you tell me. What does sine to the 4x differentiate into? You tell me that. Okay. 4 cos 4x. So that's it's if it was just a like that, yes, you are right, Hassan. If it's asking in terms of a power. Okay, so it's sine x all to the power of 4. Yes, Arib. Correct. You are correct. Okay. Differentiate normally, bring down the power by 1 times by the differentiation of sine. That's your chain rule. Yes, Tammy, I am recording this. I will email all of the access later on. Okay. There's about 15 minutes of this as well. So let's see what else we got. You know what? Right at the start I said, I don't think you can see the screen actually. Yeah, I would say there's about 15 minutes left of the yeah, Arib, you can. You don't have to simplify it. Do you think you can do this? Do you guys you could there is some integration with this as well. You know what, I'm gonna skip this. I'm gonna leave it in the PowerPoint. I'm gonna email the PowerPoint and stuff. So if you want to have a go with it, sure. Okay, quick check with some integration. You should be able to do this. You should be able to do this. I'm actually gonna make it a bit simpler. Think about what you've learned today. You got this. Go on. Who's gonna be the first one? Incorrect, Hassan. Who's gonna be the first one? No, 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 no. Not zero. Not zero. Not -3. Not 1/3. Not one. Oh. Yes, Rico. 3 ln x. So right at the beginning, do you remember how ln x differentiates into 1/x? Integration is reverse. Okay? So this becomes 3 ln x plus c. Okay? So you guys probably did x to the -1 and that, okay, you end up with x is 0. Uh-oh, that won't work. Okay? And then you just timesing by the 0, dividing, you'll just end up dividing by 0. Okay? And that's where your ln x comes in handy. Okay. Yeah, the plus, yeah, I can't lie. It's not that deep. Yes, Rico. Yeah, you showed me that. You did show me that. Honestly, on the harder differentiate integral and the differentiation stuff, they're not bothered about the plus c. So when you look at stuff like this, they're honestly not bothered. But your dx stuff is actually very important. Now I think he's talking about the in-class exam, I think. Yeah. Most of you guys, I think, are year 13. Yeah. Okay. This stuff is actually very, very simple. I'm not gonna go over part B. I'm just gonna look at part A. I don't know, you might have looked at it, you might have not. This is actually, it popped up in 2019, I want to say, or 2018. It popped in one of the papers. It popped in my year 12 exam, actually, as a mock, and I was shook, and I was like, what is this? What this basically is, it's the sum of, well, you've got this little dx here. Now, when you look at, I don't think your teachers will have probably gone over this. Yeah, integrate 2/x. But this little delta x just means that as your delta x approaches 0, that means that you would have looked at trapezium rule maybe, but when you have trapeziums like this that are like approximating the graph or the area underneath the graph, it just means that this length here approaches 0, and you end up with just infinitely small trapeziums that becomes the area underneath the graph. So this is basically saying, what's the integral between these two limits of 2/x dx? That's all it's saying. Okay, so don't be scared of this notation. It's just something I'm just throwing in there. You don't have to solve it, but it's just something I'm throwing in there because it can come up, and it has come up. Okay, but it's only come up like once, so I don't know if it'll come up again. It could. What even is that? It looks ugly in it. It's just what it's saying is you've got your trapeziums, and the length of the trapeziums is infinitely small. That's your limit. Okay, it's infinitely small. It comes from your trapezium rule. Okay, it's not necessarily your trapezium rule, but it comes from it. But what it just means is it's this. Okay, so you would just solve this integral like this, like normal. Okay, and it's just being able to convert between the two. Okay, what's trapezium rule? Trapezium rule is part of year 2. It's not that bad. You know, in GCSE, do you remember if you did at Excel maybe, for example, you have like it's like approximating underneath the graph basically. You draw a line, this is like x equals 2, then x equals 4. It's like a BTEC integration. It's basically what it is. Okay. Yeah. But I would say don't worry about it too much. It's just I'm throwing it in there because I want you to see it than to not see it. Okay. Chain rule with integration. I would say I can't lie, it's exactly the same thing, man. Okay, don't overcomplicate, just slightly adapt. Now, when you're differentiating, I want you guys actually really, really quickly differentiate this. 10 seconds. Go. You got this. Boom, boom, boom. In chat right now. Right now. Differentiate it first. Nice. Nice, nice, nice. Okay. Good, good, good. Well done, guys. So, if we know that 3x plus 2, all to the power of 5, differentiates into 15 3x. Oh, my light dropped. Oops. 15 3x plus 2, all to the power of 4. This is your, let's say the integral of this is this. Okay, and we're going to try work backwards and see what's going on. So your power, you can see it increases by 1. Yeah. You know what? It's dark now as well because my light's off. So I'm probably looking very bright. The power increases by 1. Okay. This 15 disappears. No, I'm not necessarily nil. You don't have to differentiate. I'm just showing you how this differentiation and integration relationship is so I can get you to integrate this afterwards. Okay. So you can see if you're going to integrate I got you to differentiate it because I want you to see the differentiation integration relationship. That's the only reason why. Okay. So when you integrate this, your power increases by 1. Yep. Now, for example, if you integrate 3x to the power of 5, actually, no, let's not do that. If you integrate 15x to the power of 4, this will integrate into x to the power of 5, and then you divide by the power. So that's going to be 15 divided by 5, which gives you 3. But wait, there's no coefficient behind here. So what happens? You're actually going to divide by the differentiation of this. So you're doing it backwards. Okay? Increase the power by 1, divide by the power, just like normal. But this time, instead of timesing by the differentiation, integration's reverse. So you're dividing by the differentiation. Yeah, of course, Neda. So you can see, I'm just going to let's actually put this 15u to the power of 4. 15u to the power of 4. If I integrate this, I increase the power by 1, and I divide the coefficient by my new power. 15 divided by 5, which is 3. But here, you can see that this has no 3. There's no 3 at all. Why? Because you're dividing by the 3x plus 2's differentiation. You're dividing by that. So easy way of thinking about it. Do it like normal. Divide by the differentiation that's inside. Okay. At the beginning, you were timesing. This time, you're dividing. Okay. Wait, Rika. All right. Let's look at this one. Okay. Let's actually look at the integration. I think it's easy to understand what's going on with this integral. Okay. First step. What we're going to do, 3x plus 2 all to the power of 6. Okay, we're going to increase the power by 1. Yeah? Are we happy with that? Yes, put Y in chat. Are we happy with that at the moment? Just increase the power by 1. Cool. Next, as a check, what we're going to do, we're going to apply our chain rule and differentiate this. If you differentiate this, what do you get? Yes, Neil, it is. And this is why I'm trying to get you to do it in your head rather than on paper. It is 18. So you get 18, 3x plus 2 to the power of 5. But wait, your original differentiation is actually, it has no coefficient. So that means our actual integration must be 1 over 18, 3x plus 2, all to the power of 6. And if you differentiate this afterwards, we should end up with this. Does that make sense? Scale of 1 to 10. 1 over 18, because if we are just increasing the power by 1, we differentiate it. Yes, exactly. It cancels out. If we differentiate this, that becomes 18. Yeah. Yes, sir. Yep, exactly. Okay. Scale of 1 to 10, everyone. Does that make sense? We check it, and then we apply. We just slightly adjust. 10 being easy. The trigger's bookie. Okay. I'm gonna give you guys another one. Let's rub this out. I want you to integrate integral of 4x plus 9 all to the power of 12. Go. That is a terrible pen, but what it is what it is. Differentiate first if you need to. If you know what you're doing, go for it. And as you do more of this, right, you're able to just spot those. You'll be able to just spot them really, really quick. Why have I got a Zoom notification? Where's the notification come from? Oh, it's from there. Got 1 over 52. Seeing how quick you did that. Crazy, crazy, crazy. Exactly. Okay. So 4x plus 9, all to the power of 13. I'm going to check that. That becomes the 52. I don't want the 52, so I'm just going to divide my original thing by 52. And you can add a plus c on that. Okay. And always, always, I'll just say, just check. Yeah. Slap it under 1. Yeah, basically. However, this does not work if you have something like x squared. Okay, if you have something like this, it will not work with this. So do not use that method with this. With this, how you would actually integrate it, because if you apply the same thing, right? X plus 2, x squared plus 2 all to the power 6. But then you have to divide by 2x. Or not 2x, it's going to be something else. But you're going to be divided by some sort of x. What is it in this case? I think, is it 10x? If you follow the same method? Is it 10x? I'm tripping. It's 12x. It's 12x. If you integrate this with the same method, I believe it's 12. Just correct me. Yeah, cool. Okay. Now, because you're introducing x is a variable function. The x values can change, so you can't apply that. Okay. You can only bring in new coefficients that are constants. If you bring in an x, your integral's wrong. Okay. So that will cause your variable thing to just it will not work. So how to do this in this specific one? Best situation, even with substitution, actually, this substitution will not work with this. Binomial expand. Okay, this one's binomial expansion. And as you do more integration, you'll be able to see what's the best way to integrate stuff. Okay. Now we'll finish off with these two, actually. And it is actually very, very similar. So I'd say have a go with these. Think about the chain rule that you did way, way before and reverse it. Just work backwards. Okay. Best thing to do, look at the base function, differentiate that, and then compare to your integral. And how can you slightly adjust? Okay. You're kind of inspecting it. That's the best way to do it in your head. I'm purposely not teaching you integration by substitution, because for that type of stuff, I think you should leave it for the more harder questions. E to the 5x. If I differentiate that, that becomes 5. But I need a 4. Perfect. Hassan, with 1 over 100, don't divide by the 20. So with this type of question, it's exactly the same thing, actually. Think about your base, like the base of the question. Okay, I kind of like to call it the base. I don't know what it's actually called. Yeah, of course, of course. So if you go back, the base of the question in this is your 3x plus 2 to the power of 5. In this case, you've got that. Okay, if you had a coefficient, I would say ignore the coefficient for now. You can actually, whatever constant you have, if you want to make it easier, you can move the constant outside the integral as well. That's something you can do. But I won't do that at the moment. Okay, so think about what e to the 5x differentiates to. Okay, so I'm just looking at the base function right now, e to the 5x. E to the 5x, we know, differentiates to 5e to the 5x. But we know we want 20e to the 5x. So what's the difference between them two? Times by 4. So your integral must be this. Okay, think about what differentiates into this. That's the definition of, and well, that's the relationship between your integration and your differentiation. What differentiates into this thing there? And to make that a bit easier, if you really want, you can think of it like this as well. You can make it like that, and then you know that this must be like so times by 20, and that gives you the same answer. But in my opinion, this is better. So we can't, because it's e. When you differentiate e to the 5x, do you minus 1 from the power, Naylor? Do you minus 1 from, exactly? So we can't. We're not gonna work. We're not gonna mess around with the powers here. Okay. So it really depends on the type of I don't know what's called this type of maths it is. So with ln, you're not going to decrease the power by 1 for it. Okay, the sign, if there's no power with it, you're not going to make it sine to the minus 1 suddenly. Okay. So here, same thing. What does sine to the 4x differentiate into? Four cos 4x. Nice. Now we want something to differentiate into sine x. What's that something going to be? I'm going to put the sine cos minus sine minus cos. And actually, it's minus cos. Cool. So minus cos differentiates into sine x. I'm actually going to move this minus 2 on the outside. I think it's better to do in this case. Minus 2 sine to the power, sine to the 4x, there's no power. Okay. So something differentiates into sine to the 4x. And Rico said minus cos. So that's going to be minus cos something. Well, it can't be just minus cos 4x. Because if we differentiate minus cos 4x, we end up with a 4 at the beginning. So it's not going to be just that. We have to slightly adjust this. How can we adjust it? Yes, Hassan. Perfect. A quarter. Okay, so a quarter cos 4x differentiates into sine 4x. Perfect. And we have that minus 2 as well. So we're going to times this by the minus 2. And that will give us 1 over 2 cos 4x plus c. Does that make sense? Does that make sense, guys? Amazing. Pretty light, yeah? Pretty light. You know, people struggle on this. Like, it's considered like one of the hardest topics. So on a scale of 1 to 10, chain rule and for differentiation and integration, put diff 1 to 10 and int 1 to 10. Integration, obviously, we've done less integration right now. Integration by parts is like the same as product rule, but backwards. Okay, and there's a formula for that as well. And you know what? Diff 9, integration 5. Okay. Three plus 2i. Why is the guy saying 3 plus 2i? What does that mean? That's a hidden meaning behind it, bro. And I don't know what the hidden meaning is, Hisham. Yeah. All right, that's fine. I'm happy with very very happy with the differentiation bit, and integration is actually looking good because we've done like 2 questions on it, and the fact that you guys are already at that level, I'm very very happy. You know what? I'm tempted to do this last one. I'll show you what integration by parts looks like really quick, and you can see it looks like this. Okay, it's 5 marker. How much for me? I'm gonna be back up soon, man, Rico. I'm telling you, I promise. Soon, next week, hopefully. Because you know what it is? My schedule is crazy, fam. Like, I'm actually like honestly busy. I'm not even stuck even. Yeah, real was dope. Okay, we'll finish off with this. You know, I can vouch for that, Reem. My guy. Okay. 3 minus 2x to the power of 4 all to the power of 6. What's your base function here? Just by intuition. What's your intuition telling you? What's your intuition telling you that your base thing is going to be? The bracket thing. Who says bracket thing and who says x cubed? Who agrees with Naylor? It is Naylor. Yeah, cool. Great, guys. Great contribution. Yeah, bracket thing is the base. Nice. Okay. So we're gonna look at this part here. Okay. We're gonna do some inspection and comparison. So differentiate this, what do you get? And a bit of it's about as you do more of it, it's a bit of intuition as well. How do you know it's the main function? Just I can't lie, it just looks more complicated, Hassan. That's why. Honestly, pick the one that looks more complicated. But the main reason is because, and I'll show you why. 24x cubed, that becomes 8. Minus 8x cubed. Why 24x cubed, Rico? Differentiate this real quick and tell me what you get, guys. Using your chain rule that you've learnt. 48. Yeah, that's what I was thinking. Yeah, so you should end up with minus 48 x to the power of 3. Cool. Do you guys get minus 48 x to the power of 3? When you simplify out everything. Okay, I've just simplified everything out. And that should be your final differentiation. Are we happy with that? Just using chain rule and simplified. Cool. Now, who I think it was Hassan that asked, why do we know that this is the base function? It's because when we differentiate this, it ends up with an x cubed in here. The 2x to the power of 4 differentiates into some sort of x cubed. It doesn't really matter what that coefficient is. It differentiates into x cubed. So that means that it's going to be some sort of link between the two. Well, you're right, Rico. Okay, well, we know that this differentiates into this. How are we going to slightly adjust it so we end up with our original integral? You're going to times it by minus 1 over 48. So your final integral will be minus 1 over 48 plus c. Yeah. Then multiply by, you don't want to multiply by x. Never, ever, ever multiply with x. Okay? Never multiply by x, never divide by x. Yes, that's that. First, we do your differentiation. Are you happy with that, yeah? Hassan, you happy with the differentiation bit? Just looking at your... Cool. It's not there for... Yeah, it's basically there. It's just there for vibes. But because you differentiated this part into here, well, you've already got... It just produces that x cubed. This base function produces the x cubed. So when you differentiate this, and you can check it right now as well, when you differentiate this part here, you will end up with x cubed 3 minus 2x to the power of 4 all to the power of 6. This should actually be to the power of 7, actually. Oh, I think we made a mistake here. We forgot to increase the power by 1. Forgot to increase the power by 1, guys. Oh, so that should be like so. Sorry, guys. That should be 7. That should go to 6. And the numbers slightly adjust. The numbers slightly adjust. So if anyone can just work out this coefficient really quick, and whatever that is. So when integrating with two functions, you only integrate the base. Yes, most of the time. Yes, Hisham, exactly. Add 1 to the power, divide by the derivative of the inside function. But you don't always want to do that. In this case, you don't have to divide by the when you integration, you don't want to divide by the 4x cubed. Actually, you can, but I would say stay away from that because that habit, you'll do it. You'll be like, okay, I have to do with the other ones. but you don't always want to divide by the thing. 56, perfect. Okay. You got minus 56 there. Oops, sorry. Yeah, because you cancelled out. Yeah, that's fine. In this case, I'd say that's okay. But when you're in some situations, right, you see that, okay, you have the x cubed, and then this part here may not actually differentiate into x cubed. And that's where your integration by parts comes in. Okay. And that's positive. Does that make sense, guys? I feel like I slightly just adjusted the numbers. Pick your base, increase the power by 1, differentiate, and compare. Cool. Amazing. I want you guys to try the same. Not with this, actually. I don't think this one will actually work. This one is actually by parts, I believe. I'm gonna leave that one. Try with this. It'll be positive, Hassan. I'm assuming because this part's negative 56, we want to get rid of the negative. I'm positive. You don't have to. I really don't have to differentiate. And as you get better with this, you'll be able to just do it in your head. Okay? Doing it on paper just means that it's easy to compare. Okay? For me, I found that I was making more mistakes when I was doing it in my head, and that's honestly just because I didn't practice it as much as I should have. But if you just practice it more and you strictly focus, okay, I want to be able to do it in my head. To be fair, when I was learning, I was able to do it in my head a lot more. But I just found that putting it on paper and comparing it like that just makes it easier. Okay, and it's your accuracy is just a lot better. Okay, that's the only reason why I'm putting it on paper like that. And just easy, it's easier to explain as well. Hopefully this integrates. I'm assuming it does. Hoping it does. So increase the power by 1. Make sure you do that. Yeah, because I know we do the differentiation to compare, but make sure you increase the power by 1 because that's the whole that's the whole integration process. And then we'll finish off. This will be our last question, guys. I did want to get into the parametrics, but I think I planned ahead a bit too much. Let me see. And then let me move this to my other monitor. And if you get an answer, type the answer in chat. You guys got minus a fifth. There wouldn't be, I would say there's no sine x in your final integral. There's no sine x in your final integral. Okay, let's have a look. First step we're gonna do, increase the power of our base function by 1. Okay, this is our integral side. I would say label it, and we're only going to be focusing on the left side when we're looking at final answer. Yeah. When you differentiate this becomes 5, 3 plus cos x to the power of 4 and times it by minus sine x. Yep. But let me actually make this look nicer. Like so. Okay, but in our integral, we haven't got the minus 5. We've got this part, so we're happy with this. So the only thing we need to get rid of is the minus 5. So what do? We times it by negative a fifth. So your final integral should be negative a fifth. 3 plus cos x all to the power of 5. Plus c. Great. Yay. Beautiful. All right, guys. You know what? We'll finish off there. But why do we not include the sine x? Because your this bracket here already produces a sine x. So when we differentiate this, wait, before you guys leave, I do have something to say. But before you guys leave, it produces sine x. What I did want to say is join my Discord. I'll put it in chat. Great server. Let's No, no promo today, Reeve. It was gonna be more towards the end, but I didn't get to that point. But join the Discord, yeah. Got really nice people there. Everyone's helping each other out. So yeah, it's a bit of a small community, yeah. But I want to make it. I want to grow it. So yeah, join. I hope you guys enjoyed today. I hope it was helpful. I want you guys to give me a quick scale of 1 to 10. 10, you've learned something new. Put two tens actually. 10, something new. 10, you've actually learnt and you're confident with it. 1, you're terrible. But yeah, amazing guys. Really, really happy that you guys actually came. I was like, yo, maybe nobody's gonna come. But yeah, join the Discord. It's a really, really nice community. It's a bit dead at the moment, but as more people join, I'm always active. So just drop me a message if you ever want to. What's his name? I can't remember who messaged me, but someone was like, "Yo, read my personal statement. Beautiful personal statement. They got into aerospace engineering. My guy." But yeah, beautiful. All right, guys. I'll see you later. What's my LinkedIn? What is my LinkedIn? I will put my full name if you do want to connect. There you go. Okay. Oops. Wait, did I put the yeah, I put the Discord chat in the main thing. There you go. If you do want to connect, feel free to connect. Okay. I'll probably the first guy that comes up. My name is pretty unique. Actually, no, there's another guy that's in Dubai, I connected with him. He had the exact same name as me. I was like, yo, he didn't connect back. Um, but yeah, good session, guys, today. I'm really, really happy with the fact that you guys have really, really picked up well. And I would say keep on using it in this way in terms of calculus. Okay, your teachers are going to make you put it down on paper. You can put it down on paper if you really want, but do it in your head as much as you can and flex on the rest of your class. Check me out. That's what you're going to say. Okay. Will there be more sessions like this? Maybe, hopefully. There were most people supposed to join today, but they didn't. So inshallah, hopefully we'll get some more guys that join in. So join the Discord. Yeah, I'll do the slides. And there's some extra bits here and there. Let me actually show you just because of timing as well. You can have a go at the rest of the stuff as well. This is a bit of substitution. And the parametric differentiation is actually really interesting as well. But to be honest, it's pretty easy. The hard stuff, in my opinion, is chain rule. That's the main foundation of all your integration, all your calculus stuff. If you get that down, you're gonna cook. Alright, I'll send you guys a video. I'll email the access, so I'll upload that and I'll send you the PowerPoint as well. Amazing, guys. Thank you guys for coming. And that's the end of today. Make sure you join the Discord, yeah? Make sure you join the Discord. Join it right now. Join it right now. Join it right now. Okay. I'll see you guys later, yeah? Take care. Bye-bye, guys. Yeah. Yeah, my guy Hisham, yeah, he runs a math channel. That's it, that's his place.